Good morning. It's our last lecture. Yes, indeed. It is our last lecture. So we will finish up with functions of two or sometimes more variables, but basically we will focus on functions of two variables. Those of you who may need functions of more than just two variables will evidently be able to investigate and to do things basically in exactly the same manner, nothing really different, except that we cannot actually graph a function of more than two variables, because we need two variables for the base plane, for the domain, and the third variable for the z-axis, for the function value, to depict the function, the graph of the function, as a surface. So if we have a function of more than two variables, we cannot visualize it. We cannot imagine what it looks like, because it does not look like anything at all. And so today, last time on Monday, we had a look at how to differentiate functions of two or more variables. We saw explicit differentiation, that is, we differentiate partially by one and then by the other variable. And then we had an implicit situation, the implicit functions, where we differentiate the whole expression by x, by y, by z, so by the independent variables and also by the dependent variable. And then we wrote down the actual derivatives, partial derivatives by the variables of the function. So we constructed the situation. Today, we will have enough opportunity to practice differentiation for our other purposes. And so administrative issues a bit later, because evidently there will be some who come late, and then they will seem surprised that they don't know something. Please don't forget to sign your name. And yes, take care. I will ask for another round of attendance taking later on, because it's very obvious that there are people who sign in and then just disappear, leaving the computer open, or maybe just closing Zoom, and so on and so on. So apologies to those who are forced to sign for the second time. It's all about those who are lazy, not you. And so, here we go. I will now, let me see, redo the chat a little bit so that I can see what is going on. All right, there we go. Okay, and so now, the exact differential, what that is. So first of all, let me remind you that when we find the partial derivatives, so there's a difference. Partial derivatives are, we differentiate the function. Suppose we have this function. Z is some function of two variables, in this case x and y. It goes exactly the same way, in a similar manner, for functions that are of more than just two variables. And so when we want to differentiate partial derivative, because we are only looking at the change of the function, if we hold y value constant and we make a small change only for the x value, therefore we call this partial derivative, because it's only a part of the whole thing, only in one direction. So we can also write it as dz by dx. Please note that the notation is slightly different. The letter d is written differently for this. And then we have the partial derivative with respect to the variable y. So we are holding x constant, and we are making a small change in the y direction, and see how the function changes. So it's like, yes, indeed, it's like taking a partial slope, the slope in one direction only, because in the space in 3 dimensions, you understand that as we move along horizontally, in the horizontal plane, then actually the change of the function might depend on in which direction we move. So z y. For the sake of general information, yes, it is possible to take a partial differential, a partial derivative in any direction given by a vector. So in principle, we can imagine a vector giving any horizontal direction in the horizontal plane. And yes, it is possible to find the partial derivative in that direction, but that is not within the scope of our course. So these are partial derivatives because we only consider separate directions. Now, the exact differential, remember, of ordinary function, the exact differential dy was y derivative times dx. And that also explains the Leibniz notation for differentiation d by dx, right? Because y derivative is dy by dx. dy was the differential of the function of one variable. However, now we have the function of two variables. Now we can ask, is there such a thing as partial differential? Why do I write exact differential? Sometimes it's also called the total differential, the full differential, the complete differential. That is because we are taking the exact differential, the total change of the function. So in this case, we would denote the exact differential like this. We write, yes, it's dz, differential of the function z is derivative in the direction of x multiplied by the dx. And the derivative in the direction of y multiplied by dy, the increment of dy. So it is important to note that I can write using this denotation. I can write it like this. Yes, of course. But please note that these d's are different. They do not cancel out. They are different things. dz by dx is simply a notation for derivative. However, this dx, the small step in the x direction, is something new. If we know the value of the derivative, that is the slope in that direction, then when we take a small step in the x direction, a new small step, then the function increases approximately by this. And then when we take another small step in the y direction, the slope in the y direction would be this. And then, of course, we take into account the actual step we take in the y direction. So this dz by dx, dz by dy, these partial derivatives simply signify the steepness to which the roof, the surface actually changes, the increment of the given function. So these are different things. You cannot cancel out dx, dy, dy because they are different. One of them is used to establish the derivative, and also we will find the value of the derivative. And the other one is to establish the actual step. So that is the exact differential. What does it mean really? What does it mean really? Well, the diagram is rather difficult to sketch, somewhat difficult to sketch. So we could imagine, of course, let's say, all right, let's imagine a parallelepiped. Okay, I will try to sketch and explain. I will sketch a parallelepiped. So this is the given point x0, y0, or xy in the xy plane. So this would be the given point with coordinates xy in the xy plane. So and suppose the function value is there, it's the z value. Now, if we take this dx step, this would be the dx. If we take the dx step in the x direction, the function might change approximately by this. If I take the step only in the y direction, if this is the dy, the function change might be, well, something else again. The function changes like this. But if I take both steps, it's not necessarily that we have to add these two changes, because the actual change, if I take both these steps, so actually I would go like this. The actual change is not necessarily this, and it's not necessarily this, and it's not even necessarily the sum of both, but it could be possible to have a change, well, something completely different in this direction. So we have to be very, very careful with those partial derivatives. I am basically showing you, I'm illustrating the fact that it is not the same as the increase of the function. This exact differential is not the same as the increment, the increase of the function, as we move from x to the new x plus dx, y plus dy. However, the good news is that it's the main part. If you remember anything about the differential of the function as such in 2 dimensions, remember we had this graph. We said, all right, let's make a change dx or delta x in the x direction. And we see how the function value changes, well, by this distance, the actual function change. But we assume, for the sake of simplicity, for the sake of approximation, we take only the principal part, only the part of the increase of the function, not from the old value to the new value, but from the old value to the value on the tangent line. That was the differential of the function, and actually from this geometrical interpretation we had this differential of a function of a single variable. Now with two variables, we basically take the tangent plane, because if we have the graph, which is a surface, and I have not sketched anything like a graph here, there's no graph, no surface, there's only one point. This is only the one point on the graph. I haven't sketched the surface. So instead of, when we move to some other point nearby, point, we can basically, instead of estimating the actual change of the function, the actual increment of the function, we take the point on the tangent plane. We will see what a tangent plane looks like later today. I have illustrations. So basically, I could consider the actual change from the old z value to the new z value up there. But what I basically do is I think of the tangent plane drawn at that point. I should probably mark it with a different color. At this point, instead of taking the actual value of the function, we take the value on the tangent plane. Imagine we have a curving surface and we have drawn a plane touching that surface at this point. So we take the approximate value on the tangent plane and the increment, the approximate increment, the principal part, is this exact differential. This is what the exact differential actually means. Simply the increment. So in general, we understand that when dx tends to 0 and dy tends to 0, then the increment of the function is approximately equal to the differential, to the exact differential, the total increment. If you remember last time, we had this total increment of z, which happens if we take both these steps horizontally in the horizontal plane. That would be the actual increase of the function. But we say if these steps are small, if these steps are really small, then this is approximately that. Again, you have probably used this in physics lab to estimate the error in a formula, for example, that depends on two variables. You have probably used this, at least those of you who take physics lab, who have physics lab. So let's see what's next. Yes, I will now erase my ink this because I have this printed in a nicer way, so more visible, more obvious. So this is the exact differential. It's the principal part of the increment of the function if we move by small steps in y direction and in x direction. But that's in small steps. The ever-present question in mathematics is, what does it mean sufficiently small steps? How small is small enough? So basically, we would need to evaluate the relative error, the relative accuracy, which I leave for your physics lab for your practical applications. And so dx is the same as delta x, the small step, and dy is the same as delta y, a small step in those directions. So that's why I said tends to 0. So I will, okay, I wanted to erase the red part because it's rather difficult to see. And so for 3 variables, if we have, for example, a function of 3 variables, u is a function of x, y, and z, then the exact differential would be, of course, the 3 partial derivatives, each multiplied by the corresponding increment of the independent variable, and all of them added up. That's the exact differential. Exact because it takes into account all directions. All directions. Of course, in this last case, with 3 and more variables, as I already said today, it's impossible to imagine, it's impossible to graph. We cannot think of a tangent space to some strange 4-dimensional object. We can think of a tangent plane to a 3-dimensional surface. We can think of a tangent line to a 2-dimensional curve, but if we have more dimensions, here we have 4, because u is the 4th dimension, of course we cannot imagine what it looks like. It doesn't look like anything, but the exact differential as such exists. It is used to estimate, to approximate the function value. So if I know the function value at my given point, then by adding the differential, I can approximately estimate the value of the function at that new point. Approximately, yes, of course, it's not accurate, it's not exact. The differential is called the exact differential because it takes into account in the 2-dimensional case, in the 2 variable case, it takes into account both independent variables. In more than 2 variables, it takes into account all independent variables. That's why it's called exact. Exact or full or total differential, as opposed to partial derivatives. Partial derivatives characterize only separate directions. The exact differential characterizes basically the total change, the general change of the function. Let's have an example. The example is easy to do. So remember what we have to do. I'm reminding you of the formula. So dz is z derivative by x times dx plus z derivative by y times dy. So let's do those derivatives. Derivative by x would be, remember we are holding y constant. So x derivative is 1. So the derivative of 2xy squared is simply 2y squared. The derivative of minus xy is, of course, simply minus y because it's x derivative plus, and 3x squared derivative is 6x. We actually had this very same function, I think, on Monday as well. And derivative with respect to y. Y squared derivative is 2y. So we have 4xy minus xy derivative with respect to y is minus x acting as a constant, and the other two are constants with respect to y, so we have to stop there. And now the dz. It is evidently derivative with respect to x, partial derivative with respect to x, 2y squared minus y plus 6x dx plus derivative with respect to y, 4xy minus x with multiplied by dy. And that's it. This is the exact differential of first order, because we are only using the first order derivatives. For the exact differential of the first order, like this. So actually now, if we have a point, a good point where we know the function value, and we want to establish the function value nearby for small dx and small dy, stepping out of our point just a little bit in each direction, x and y direction, then if we actually have the derivatives of that function and we find the value of that derivative of both partial derivatives, like the slope in the particular direction, then we can use all these numbers to actually figure out the approximate increment of the function, which is the exact differential. And then second and higher order exact differentials. Second and higher order exact differentials. So the first order exact differential is just for the sake of reminding. You don't have to rewrite it and copy it many times. So the second order exact differential would mean take this and take the differential of this. So the second order differential would be the differential of this. The differential of something means derivative times dx, derivative times dy. So what I have to do is I take dz, differentiate and multiply by dx. I'm finding the exact differential of this. So this dz is what I need to differentiate by x with respect to x, and then I need to differentiate this partially with respect to y and multiply by dy. What happens here is, yes, I will rewrite it. Z derivative by x dx differentiate by x dx plus, yes, the second part still here because I am splitting it into two parts. So z derivative by x differentiate by y dy, that would be this part differentiated both by x and by y, and now I'm taking care of this part. I will differentiate this by x and by y. So it is derivative by y differentiated by x dx, and sorry, no, just a moment. Yes, that's okay. Sorry, I forgot the other d's. Sorry. Dx, I forgot the dy here and dx. That's the thing. That's where it started looking bad. So this is the y, no, dx, I'm sorry. Now this is where I went wrong. So one warning for everybody: learn from my errors. Well, this is my error because it was my absent-mindedness, not that I don't know it. But be careful. You should never really never lose the dx. Next semester in integration, it will be crucial. It will be important that you remember to write the dx and dy wherever it's necessary, because without those, you will fail with integration. Nothing will work with integration or with differential equations. This is going to be, otherwise it's going to be bad. So now I'm taking this other part, this part, z derivative by y dy and differentiate by x dx. So I have done I have taken this and differentiated by x and multiplied by dx. So far, I have this. Now plus the second part. Again, I take the same thing and now I differentiate by y. I take z derivative by x dx, differentiate by y, multiply by dy, plus z derivative by y dy, differentiate by y dy. So see what happens now. See what happens now. We have dx, which does not depend on the function. So this acts as a constant again, even though it's dx, because the function, what depends on the function is only this z derivative of x. This is the only part of the function. This is the only thing that we can differentiate because it's the only thing connected with the function directly. This is simply a chosen step. So differentiate the second time by x. So we have second derivative both times by x, and dx times dx now is dx squared. Now the next part, the middle part, C, y derivative by y, partial derivative by y. Sorry, differentiated by x, and partial derivative by x, differentiated by y. Remember that it's the same thing. So we have two of them identical. We have dy times dx. Here we have times dx times dy. The derivatives, the mixed derivatives, are equal if they exist, remember. So basically, I have two identical terms. I have to multiply by 2. 2 mixed derivative xy and dx dy. And we end with the second order partial derivative by y. And we see dy squared. So this is the second order exact differential. Written perhaps in a nicer way. But it's the same thing. You see the second order partial derivative both times by x multiplied by dx squared. Second order partial derivative by z both times both times by y multiplied by dy squared. And double mixed derivative by x and by y. Second order mixed partial derivative by x and by y doubled, because one comes from differentiating by x the partial derivative by y, and the other copy comes from differentiating by y the partial derivative with respect to x. So that's how they actually show up, two of them. We get two of them here, that's this part. And finally, second order partial derivative by y dy squared, which I already said in the end. I named the first term, the third term, and in the end, the middle term. If there's a need to find more higher order partial derivatives, those of you who are familiar with counting principles and Pascal's triangle, hopefully at least some of you are familiar with Pascal's triangle. If you are not, then at this moment, I will not explain because there's not enough time. Do you remember the next row? How is the next row created in this triangle? 1, 4, 6, 4, 1. So every number in this triangle is obtained by adding the two numbers above it. So basically, the third order partial derivative goes like this. That is, the third order partial derivatives, first all 3 times by x, dx cubed, then twice by x and once by y. It happens 3 times. If we did another partial differentiation round with this, we would see that we have, if we differentiate this by x, we get 2 copies of this. If I differentiate this by y, I also get one copy for this. So this explains this adding principle, actually. And the fourth order exact differential would be fourth order derivative only by x. Then we would have 4 mixed derivative by 3 times by x, once by y. Then we would have 6 copies of twice by each, and so on and so on. So these exact differentials are of less use. It's simply for the sake of definition, but I think in the homework, you have the second order exact differential to write down. So in the homework, you might need to write down the second order exact differential. As you see, all you need to do is find these second order partial derivatives, both times by x, mixed derivative, and both times by y, and then simply write it down without any problem. So if in the homework, in the midterm exam, for those of you who have to write the final exam, you are asked to write a second order exact differential, then you simply do the necessary derivatives, second order derivatives, and just write it down using the formulas that you get. And that's it. Now, let's do some exact differentials. This question is from your exercises from the lecture file. Let's do the exact differential for this. The exact differential, if I don't mention the order, it means first order exact differential. If I say second order, then of course you have to do the second order. So in this case, we are dealing with the first order exact differential because it doesn't say second order. Be careful, don't do too much because that's a waste of time. You're wasting time if you are doing unnecessary things. And so the derivative of z by x with respect to x, or if you like, but then you have to write the correct d. You have to do the correct spelling for d. So the derivative of ln u, remember, is 1 divided by u times u derivative. So in this case, it would be 1 divided by x squared plus 3y squared times derivative of this expression, of course, only by x. So it's just 2x. That's it. The derivative with respect to y, so derivative with respect to y, is again the same. Divide by x squared plus 3y squared and multiply by the derivative of this expression, which is by y. So that would be 6y because x squared is a constant in this case, supposed to be a constant. And now the exact differential. dz is 2x divided by x squared plus 3y squared. You can write dx if you like here above the line. Well, I write in principle here so that you see the structure of the exact differential. I write dx after the derivative, not on the same line, so that you see the structure. So you see the derivative with respect to x times dx plus derivative with respect to y times dy. But as I said, you may easily move, if it's easy for you, you may write it there up on the line, no problem. What also is possible, yes, it is possible to take the common factor out. Some people sometimes wonder if it's allowed. Yes, you may, for example, take 2 divided by x squared plus 3y squared out of parentheses and then leave what is remaining. X dx plus 3y dy remains inside the parentheses. Yes, this is allowed. This is possible. You may write it like this. I am not requiring it. What I need to see is basically, I need to see this part. I need to see that you recognize, first of all, that you can differentiate. Secondly, that you know what to put where, how to put things together. Then, if you want to simplify it to this, doesn't look much simpler, right? Then you may. Now the second order partial derivative. Now this is the second order partial derivative, see? So let's find that. Okay. So I will use the short notation because this is how we write quickly. And those of you who unnecessarily waste time during a test using d by dx, copying from Wolfram Alpha, Photomath, or what other application you find, this is how I know that you are copying. Because you spend a page and a half on a question that could be solved in 2 lines. That's how I know. Unnecessary waste of time and unnecessary things that you do and write. That's because your application tells you. And that's something I really, really, really dislike. Professionally, not personally. Personally as well, because I hate cheaters. Okay, back to our example. So we have to differentiate this by x. So sine x at this moment is a constant. It doesn't change. Sine y is a constant. So differentiate by x, we get cosine x times sine y. Because sine y acts as a constant here. Derivative by y would be sine x is a constant. And sine y differentiated is cosine of y. Now we need those second order partial derivatives. So the second order partial derivative both times by x, and don't forget to write x twice if you use this notation, because the variables are important. It's important to see how we differentiate. So again, sine y is a constant. Cosine derivative is negative sine. So I have minus sine x, that's the derivative of cosine, times sine y, which acts as a constant at this moment. Next, second order derivative, let's do the mixed derivative, xy, which will be, of course, the same as yx. You can choose, differentiate the first partial derivative, that is the one by x with respect to y, or take this and differentiate it with respect to x. There will be no difference actually. So I will in fact take the x derivative by x, differentiate by y. Cosine x remains the constant. And if I'm using this version now, and if I differentiate by y, sine y derivative is cosine y. And finally, the second order partial derivative, both times by y. So sine x is a constant for this. Cosine y derivative is minus sine y. Notice something. The two partial derivatives that are of the same second order partial derivatives of the same variable are basically identical. And so the second order differential, d to z, we take this multiplied by dx minus sine x sine y dx squared plus double mixed derivative 2 cosine x cosine y dx dy, both of these increments, and finally minus, because this is negative, sine x sine y dy squared. So you see here we have, this is the corresponding second order partial derivative. So you have to find them. You have to do this part on top, and then you simply write down the second order differential. So finding the second order differential or the first order exact differential is nothing. You always will need to differentiate. You always will need to find the partial derivatives, but then all you have to do is put everything together. Simply write one line putting this together, it's not longer than this. All right, so how to use the exact differential to approximate a function? So basically, let's remember that the function f, or function f of x and y will be approximately equal to the original function at whatever point we can know its value, plus the exact differential of this function, but yes, established, estimated at that same point. Or z is approximately equal to z0 plus dz. That is, supposing we know the function value sum at some point, some function value we do know, and then we consider the change of the variables x and y and estimate the increase of the function. So this is the approximate increase of the function. And integrate. Integration of this differential is integration in two variables. Careful, it's a double integral. So basically, you have to be very careful. This will come next semester when you get integration. When we have double integrals, you have double integrals. You will have the second order differential, perhaps not, but basically it applies to solving differential equations. There is such a category of differential equations that are called differential equations in exact differentials. Then yes, you will be able to find the original function z when you integrate, but there's a specific method. It has to be done very carefully. So next semester, the professor will show you how to do that, but yes. All right, so in this case, suppose we have a function square root of x squared plus y squared. It seems natural because there are two big numbers involved. Big, well, big, like big, not really big. Why is this a good function? See, if we take the point x0 is 6, y0 is 8, then z0, the basic value of the function, can be found because these are familiar numbers. This value is well known from Pythagorean numbers. It's 10. So we know that at 6, 7, this function value, the value of this function is 10. Now, if I increase x just a little bit, and if I increase y just a little bit, the question is, how much does the function value increase? What is the value of the square root, or at least approximate value of the square root? And this is what we will be doing. So we know that for the exact differential, let's say approximate or to evaluate the increase, the approximate increase of the function, we have to find the exact differential of this function. So first of all, let's find the derivatives. So the first derivative by x is, of course, 1 divided by 2 square roots times the derivative of the interior function with respect to x, that's 2x, and 2 disappears. And derivative with respect to y, again the same, 1 divided by 2 such square roots, x squared plus y squared, times derivative of the interior function, chain rule, interior function differentiated by y is 2y, and these again disappear. So the thing is that I could write the exact differential now as x over square root x squared plus y squared dx plus y over square root x squared plus y squared dy, simply copying the exact differential. Now I need to evaluate it. I need to evaluate it so that I can have this number to add. So I can have, like, I see how much the function increases, approximately, of course, approximately. So we do this, we evaluate this, of course, this happens at the point x0, y0, so for x values 6 and 8, but we also, let's remember that dx is actually 0.003. dy, the increase of y, is 0.04, because we are looking at this point, 6.03, 8.04. So this is only the point from which we start. Generally, how do we know from which point to start? What to choose for x0, y0? We choose values such that, first, are close to our points, close to our values, and secondly, for which it is easy to evaluate the function. So, two conditions: close to these values and such that it is easy to do. And so at this point, now we see the exact dz value would be. Let's put in the values of x and y. So x is 6 divided by square root of, well, we know that it's 10 already, we know, we had it. By the square root of 100, sorry, it's 10. The square root itself is already 10. So 6 over 10, I know because this is 10. That's how I know to put 10 in there, times dx. But dx is 0.03. Similarly, with y, we have y0, that's 8, divided by 10 again, times dy, which is 0.04. So we see 0.6 times 0.03 plus 0.8 times 0.04. This is 0.018. This is 0.032. So we see 0.05 as a result. And so I can say that this is approximately 10 plus 0.05. This is the dz value. It's not the exact increase of this function, but it's approximately established, estimated using the exact differential. So 10.05. This would be the approximate value. And if you check it using the calculator, you will see that it seems to be a good approximation. Similarly, when you need to establish the error of calculation in your physics lab, for example, then you do something similar. You only don't perhaps use this, but you say, okay, we approximate the value at this, and the absolute error is no less than, perhaps approximately equal to 0.05. If you know the errors of measurement, for example. All right, so this was about differentials, the exact differentials. Now, let's say, finding minimum maximum points, finding tangents, normals, and such like. The tangent plane and the normal line to the surface. Well, I didn't risk myself sketching, so I actually give you a general idea. So we have a surface, this curved surface, and then we have a point at which we imagine you can put a flat sheet of something, well, something not flexible, a flat sheet of metal, for instance. You can put close to the surface so that it touches the surface at one point. That's the tangent plane, similar to the idea of the tangent line in 2 dimensions, tangent line to the graph. So a plane, you know, a plane has a normal vector. A plane has a normal vector, as you see, Okay, I will take something colorful. A plane, you know how to write the equation with a plane having a normal vector. So if the normal vector is A, B, C, then the point M0 has coordinates x0, y0, z0 on the surface, then of course you know that the equation of this tangent plane, if we only know ABC, of course, if we only know ABC, of course, then the equation for this plane would be, I am reminding you from analytic geometry, which you should know by now, plus CZ minus Z0 equals 0, then simplifying using the numbers, right? And the line passing through this point is called the normal, or normal to the surface. The normal is characterized, of course, by its direction vector, and the direction vector is, of course, the same. So that would be, this is the tangent plane. And the normal line is the line perpendicular to the surface. So now you see that we can write this using the same numbers and the same vector, the same point, and the same vector. The only question remaining is, what are these numbers ABC? How do we find these numbers ABC? How do we find the, let's say, the direction perpendicular to the surface? And that's what we will do right away. So we will start by assuming that the surface is given implicitly. This is implicit equation. So we still consider that z is a function of x and y. But we have a long expression on one side. Then actually it turns out an interesting thing, that if you take this expression f, this big expression, this implicit equation, on the left hand side, on the right hand side we do have a0, and if we differentiate this with respect to all three of them, so we find the partial derivative with respect to x, we find the partial derivative with respect to y, we find the partial derivative with respect to z, then interestingly enough, at this certain point, so we suppose that we have a point on the surface, x0, y0 are the values of the independent variables, and z0 is the function value actually. Then if we find the derivatives, the partial derivatives, specifically using numbers for this point, then guess what? You have found the coordinates of that normal vector. So basically, now we see the meaning of the partial derivatives of a function. The partial derivatives, including the partial derivative of the function value z itself in the implicit equation, are actually giving you the direction in which the surface is curved, mostly at that point. So the direction perpendicular to the surface. The derivatives, the three derivatives of the implicit equation by all three variables, x, y, z, give you the direction in which the surface is curved most. The strongest curvature is in this direction. The normal vector to the surface goes in this direction. This is the meaning. So you don't have slope as such as we had. The meaning of derivative is the slope in two dimensions. However, if you did it implicitly, you would still get the normal vector for the curve in two dimensions. If you wrote the implicit equation for the function, and if you did it by the variables x and by y, the partial derivatives, you would get the normal vector in plane in two dimensions. So this is the, let's say, the most obvious meaning of the values of the derivatives. So of course at m0 at the specific point, and I think I had it printed. Yes. Sorry, I have to erase this. I will erase everything I wrote. So basically, we already wrote the tangent plane. So we don't write it in terms of this. It's easier if you find this is a vertical line, and I write at the bottom that we are evaluating this at the point M0. So this is A, this at the same point M0, this was B, and the derivative by Z at the point M0 is C. So for the tangent line, we already had the equation. If you wrote it down, you already have it. And for the normal is a line. Tangent plane, yes, but normal is a line, only one direction. We use the point M. We use the point M, that is M0, the given point on the surface, and we use the derivatives, partial derivatives at that point, the values of the partial derivatives at that point. So basically, the normal vector would be the vector f derivative with respect to x at m0, f derivative with respect to y at m0, f derivative with respect to z at m0. That's the normal vector. But in principle, it's much easier to do it separately and then write down the normal vector. Writing like this is not economical. It's not economical, and it's not very, well, it's correct, but it's not easy to understand. It's much easier if you do the derivatives separately, evaluate them separately, and then simply write down the vector n. And of course, you can find the normal unit vector as well. That is, if you take this normal vector and divide by its magnitude. So we are connecting back to the second unit, back to vectors, and back to analytic geometry. As you may have noticed, we are connecting back to the previous units all the time. Yes, let's try this. Let's try this. Tangent plane and normal. So we have this long expression, which is the function f, the equation f. We still think z is a function of x and y, but it's given implicitly. It's not written in this form. It is written in the form an expression containing x, y, z equals 0. So we take this expression f, the left-hand side, and differentiate away. So the derivative with respect to x is, let's see, 8x, 2y squared constant, nothing, minus 3z squared constant, nothing, plus xy, derivative by x is y, yz constant, nothing, plus x, that is, derivative is 1. The derivative by y with respect to y, 4x squared constant, derivative 0, for 2y squared, derivative is 4y, z squared is constant, xy derivative by y is x, yz derivative by y is minus z, because there's a minus sign, x derivative, 4 derivative, those are zeros. And finally, the partial derivatives with respect to z, first term 0, second term 0, third term minus 6z. Fourth term, 0. This minus y when we differentiate by z. And the remaining parts again are constants for z. So in this case, derivatives are 0. Now let's see. A is, and now let us put these values for x, y, z. So that would be f derivative at x at, we can write 1, 1, 1. In fact, we don't have to use the vertical line. We can put in the coordinates x0, y0, z0. And that will be 8 plus 1 is 10. B, so you see, this is easier to do if we do it separately. It's orderly, everything is obvious, everything is understandable. At 1, 1, 1. And so we have 4 plus 1 minus 1 is just 4. And the coefficient C, F derivative at Z, 1, 1, 1 is minus 6 minus 1 is minus 7. So now we can write down the equations for the tangent plane and for the normal. All we have to do is write them down because we have done all the work. We have found the derivatives. We have evaluated those derivatives at the point of interest. Now all we have to do is simply put down the answer. So we have 10 times x minus 1 plus 4 times y minus 1 minus 7 times z minus 1 is 0, or we can write 10x plus 4y minus 7z is, this is minus 10, this is minus 4, that's minus 14, minus 14 plus 7 is minus 7, move to the other side, 7. So this might be an equation for the plane. We can also leave the minus 7 on the left-hand side, as we usually do in analytic geometry. And the normal line, we use exactly the same expressions, remember, x minus x0, y minus y0, so it's still x minus 1. And now this normal vector, ABC, serves as the direction vector for the normal line. And that's the normal line, the normal. So this is the normal, and this is tangent plane. And that's it. So again, the basic work for second order, for functions of two derivatives, whatever you need to do, you always need to do partial derivatives. So that's the basic thing. After you have found the partial derivatives, then you have to follow the rules, follow the formulas. Please note that all the formulas are in the second midterm formula sheet. And for the final examination, you simply take these, the first midterm, second midterm formula sheets combined. That's all. That's all. So the formulas are there. And so, well, I already did all that. For explicit functions, sorry. This was for implicit function, that is, if we have this kind of expression. So for an explicit function, the explicit function is, well, z is some expression of x, y. So I can change it theoretically. Generally, you will not need to change it because you will have, again, a ready-made formula. So I can think of this as f of x, y minus z is 0. So now this is this f expression of x, y, z, right? I simply move the z variable to the side where we have the formula. And now, see, if I differentiate, see, notice, f derivative by x is actually the z derivative by x, because this is not, if we are differentiating now the whole expression, the difference between implicit and explicit differentiation. In implicit differentiation, we do not use the chain rule for different variables. So for implicit differentiation, we take each separately, each variable separately. Partial derivatives by each variable separately. So we don't have to do anything else. So this is just this, because we see this. We have it here. We differentiate it by x. That's it. Z derivative with respect to x. Remember, z pretends to be a constant at this moment, so nothing. Now, the derivative by y with respect to y, again, the same thing. Only this part, only the part f of xy can be differentiated. So it's z derivative by y. And finally, f derivative by z with respect to z. This does not contain z. Only this has the derivative of minus z is minus 1. So you see that basically we do the same thing. For explicit function, it's easier. Why did I leave it as a second explanation if it's easier? Because it follows directly from the implicit differentiation. So it's easier to say it like this. So the derivative of z at the point of course x0, y0. This is the derivative of z by with respect to y, again at that point x0, y0, and c is simply minus 1 in this case. So basically we do the same thing, only because the function is already explicit, we have a little bit less differentiation to do. It's simpler. Let's have a look at an example. So see, you have actually the function z is given explicitly. The function z is given explicitly as a function of x and y. So, all right, derivative by x. Now, this type of function, we have been doing it so much that you should be able to do it very, very quickly. X squared derivative 2x minus 3xy derivative is minus 3y. Y squared derivative 0 minus 2x derivative is minus 2. And these are constants. Derivative with respect to y. X squared is a constant, minus 3xy derivative by y is minus 3x. 4y squared derivative is 8y, 2x derivative 0, 3y derivative is plus 3. 2 derivative as always is 0. And so at this point, I see that a is z derivative at 2, 0. Put 0, x is 2, y is 0. 4, 2 by 2, 4 minus 0 minus 2. 4 minus 2, that is, it is equal to 2. Coefficient b is the partial derivative with respect to y at that same point, and that is minus 3 times 2 is minus 6, plus 8 times 0, 0, plus 3 is minus 3. And we know that c is automatically minus 1. You don't have to do it. We know automatically. In this situation, for explicit function, we have c is equal to minus 1. And to be able to write the equation for the tangent plane and normal, we do need to find the z value. So we have 4 minus, as soon as we multiply by y, it is 0. As soon as we multiply by y, it is 0. Minus 2 times 2 will be 4. This is 0, and this is 2. So it's 4 minus 4 plus 2 is 2. So we find the third variable value, the third coordinate of the point on the surface, the function value. Okay, somebody is leaving. All right, somebody's leaving. Does it always remain minus 1? No, only in this situation where you have a function explicit. So if z is written simply only in terms of x and y, you see, there's no z here on the right-hand side. If you can write z as an explicit function, then the third coefficient will be -1 always. If, on the other hand, you have a mixed expression of all three variables equal to 0, then in this case, you have to do the 3 partial derivatives. It's only in this case when we have explicit functions. For implicit functions, you have to differentiate 3 times with respect to each of variables separately, and then you will have a different value. But in this case, it's -1. In this particular case, it's -1, yes. Whenever you have z is an expression of x and y, it is -1. And so the third point is found. So the point M0 now is 2, 0, 2. And we can write the tangent plane is 2 times x minus 2 minus 3 times y minus 0 plus 2, sorry, not 2. I was careless a little bit. -1. It's -1 there. It's the coefficient. So -1 times z minus 2 equals 0. I write down 0, and I write down the one coefficient, the unit coefficient. Why? So that you see what is going on. Yes, of course, during the examination, you can easily just write minus and do things easily without the 0. However, if you write it like this, if you write y minus 0, and if you write -1 times something, you demonstrate that you understand what is going on there. But it's up to you. So of course we can write 2x minus 3y minus z. Here we have -4. 0 and +2, that's -2. Of course, we can change it. And the normal, we have x minus 2 over 2, y minus 0 over -3, z minus 2 over -1. And that's it. Nothing else needs to be done in such a standard classical problem, the classical task. All right. Now, how to find the local minimum, local maximum points of a function of two variables. So now let's see the situation, what it looks like. Imagine we have a surface where the function has a local maximum. A local maximum basically means that there is some neighborhood, some small circle, it might be very small, around the point M0. So the local maximum basically means this is the maximum point, M0. Coordinates at this point are x0, y0. And at this point, we call this the local maximum point if, of course, the function value is greater than anywhere else in that neighborhood. This neighborhood could be extremely small. The only condition is it must exist. There must be some. There must be some. There must be some neighborhood, maybe very small, such that at every other point of this neighborhood, the function value is smaller. It's intuitive, so you can understand what a local maximum of function means. And similarly, a point is a local minimum. Again, if we have some neighborhood about this point, around this point, even if it's very small, it has to be on all sides. It doesn't, M0 is not on the boundary, it has to be inside some very small neighborhood. It could be larger if you like, but at this point it's acceptable. And then you see that at all the points except for M0, the function values are greater. So we call it the local minimum point, the local minimum value of the function. That's basically reminding you what it might mean. So the top of the hill or the bottom of a hole, the bottom of a lake, perhaps. How to find them? So the critical points Suppose we have a function, and we will now consider only explicit functions because it's easier for those. However, understanding implicit differentiation, it is possible to do for other functions as well at this moment. At this moment, we will only stop at explicit functions. So, all right, an extremum point, that is minimum or maximum point. At these points, both partial derivatives are zero. Both partial derivatives are zero. Why so? Because the tangent plane at this point, as you see, is horizontal. The tangent plane is horizontal. That means the vector, the normal vector, is strictly vertical. So it has this z component -1, the normal vector, right? It has this z component -1, but because it's strictly vertical, the first two components of this normal vector are zeros. That is, both partial derivatives are zeros at this point. So the partial derivative by x and partial derivative by y is zero at this point. If we have this smooth maximum point, the horizontal tangent plane. And that's why we have this condition. Both partial derivatives, both first order partial derivatives must be zero, or maybe they don't exist. If we have a spiky peak, like something like really a mountain peak, a spike, then in that case, of course, the derivatives would not exist at that point. But we will only consider these stationary points, only these horizontal extremum points. So the partial derivatives might not exist, but we will be mostly interested in these. The thing is that, of course, it might be possible that the partial derivatives are zero, but it's not an extremum point. Let's have a look. So we can have this situation. We can have a maximum point. We can have a maximum point with horizontal tangent plane at that point. We can have a minimum point with horizontal tangent plane at that point. And then we could have a point like this. This is the graph of an actual function, z equals x squared minus y squared. It's called a hyperbolic paraboloid or parabolic hyperboloid, whatever you like, because when we look in from the x direction, you see the sections are parabolas. If you look in the x direction towards the origin, see what you see are parabolas. If you look from this way, this is a parabola. The next section is a parabola. Here we can imagine a section that's a parabola. But if we look from the y direction, what we see, this curve, it's a hyperbola. It's a hyperbola, a branch of hyperbola. This is a hyperbola. On the other side, this would also be a hyperbola. So this is a saddle surface, as you can imagine. And at this point, for example, at this particular point, I can see that, yes, the tangent line horizontally with respect to x is horizontal. The tangent line with respect to y is also horizontal. So this actually means the tangent plane, yes, it does intersect the surface, but it's horizontal. The direction is horizontal at that point. However, it's not minimum, not maximum. It's a saddle point. It's a saddle point, which means that it's not enough to find the points where the derivatives, the partial derivatives, equal zero. But that's the same thing that we had in a single variable function. Remember, if the derivative is zero, the tangent is horizontal, we could have a minimum, we could have a maximum, and we could have an inflection point. We don't call them inflection points in 3 dimensions because that's more complicated than that. But you could call them saddle points. Also because in the one variable function, only one derivative is involved. in two variable functions, you see that two derivatives, two partial derivatives are involved. So it is a little bit more complicated. It's not a perfect analogy. It is not a perfect analogy with one variable function, but still the idea is more or less the same. It's not sufficient to have a horizontal tangent plane. It's not sufficient to have a horizontal tangent plane. And therefore, when we find those points where the tangent plane is horizontal, we also need to decide which kind of point it is. Now, how to do that? So how to find the extreme? How to find the extreme point? So what we do, the first thing is evidently, I need the white pen. The first thing is evidently, let's suppose we have a surface which is described by an explicit equation. So what we do is, of course, first of all, we find just a moment. Slight crisis. Okay, the same thing again. Eraser, erase. Now it will work. Okay, so what happens here is we find the first derivative. Well, both of them partial by x and by y. And we say we need these derivatives to be equal to 0. In principle, you will have a system of equations. We say, okay, I want a point where the first order partial derivative with respect to x is 0 and the partial derivative with respect to y is also 0, because I want this horizontal tangent plane so that the first two coordinates of the normal vector are zeros, right? And if I solve this, solve and find critical points. Okay. So you will find critical points. These will be the points where the tangent plane is horizontal. Now we need to check somehow. We need to check whether this critical point is minimum, maximum, or nothing. Now let's remember what happened in a one variable function. We were using basically the second derivative. Remember, if we had a minimum point, the second derivative was positive, the function was concave up, happy. If we had a maximum point at this point, then we saw at this point the second order derivative is negative, set function. And then if the second derivative was 0, we couldn't say anything at that moment. We had to do more investigation by other methods. So there is something, but yes, we have 3 different second order partial derivatives for this function. Now what to do here? This is not enough to have one derivative. So what we do is we find the second order partial derivatives by x. Okay, not this. The derivative, second order derivative, both times by x. At this point, at this critical, okay, I will write x0, y0 here, the critical point. Hypothetical, let's say potential, possible extremum point. Then we put the coordinates in the second order partial derivatives at x, y, zeros. It is of course the same as the partial derivative, first by x, y and then by x. And we find the second order partial derivative both times by y. These are numbers now. So we rename these numbers. This will be A11. This is A22 from second. And this will be A12 or also A21. And guess what? We make a determinant. We make a determinant. So we write now the determinant using these numbers. A11, A12, A still 1, 2. I'm writing 1, 2 here as well because it's the same number. And A22. So by default, these two numbers on the second diagonal will be equal, same number. So of course we have A11, A22 minus A12 squared, right? We have this. And now we consider this determinant. This determinant, totally taken together, actually characterizes, in many cases, not always, the nature of this potential, of this critical point, of this possible minimum or maximum point. And so now, first of all, if the determinant is positive, then the extremum point exists. It is an extremum point. If this determinant is negative, then it is a saddle point, no extremum. It's a saddle point, no extremum. And if the determinant equals 0, the question remains open. This method does not give an answer. We have to actually investigate. For example, you could compare the function values if you change x a little bit in both directions. You might check that perhaps for holding y the same with a little change for x values, you see how the function perhaps is greater on both sides, and then you do the same in the y direction and simply check things. And so the question is no answer to this question. But it's simply that you have to use other methods. You have to investigate perhaps more explicitly how to investigate the neighborhood of that point. And here, extremum points. Now, how do we know whether it's a minimum or maximum? Well, we just look at A11. If A11, the number A11 is negative, then we have a maximum point. If A11 is positive, then we have a minimum point. Similar to the single variable function. So see, negative second order derivative, sad, looks like a maximum. Positive, happy, concave up, looks like a minimum. Why do we only need to check the one number and not everything? Simply because, see, we subtract a square. If the determinant is positive, this expression must be positive. That means that this product must also be positive. This product must also be positive. That means the sign of A11 is exactly the same as the sign of A22. That's how. That's why we only check one of those points. Basically, the whole general idea is that the total, let's say, total curvature, total curving in XY direction is stronger than possible curving somewhere in between in other directions. It compensates. It's more than possibly flatter curve in a flatter surface in other directions. And so the general plan, don't worry if you didn't have time to copy all that. I'm repeating everything. So the method, establish stationary points, that is the points where the tangent plane is horizontal, by solving this system. Just find the derivatives, write a system, solve it. If you're lucky, the system is linear. If not, then the system is more complicated and you have to employ some methods. Next, find the second order partial derivatives at the point where you solve. So the solution, I will repeat, this gives us critical points, for example, x0, y0, or more than just one, then you find the second order partial derivatives, as you see, at these points, 1, 2, 3. So again, all 5 interesting derivatives, partial derivatives. So basically, there's very little chance that you will escape having to find 5 partial derivatives. The 2 first-order partial derivatives and the 3 second-order partial derivatives. Whatever problem you have, you might have to find 5 partial derivatives for this function, for any function, for any function of 2 variables. Then you find the determinant, establish this determinant. See, I'm just repeating what I wrote on the board. And then if this determinant is positive and the first element in the corner is negative, then you have a local maximum point. Then you have a maximum point. If the determinant is positive, but that first element is positive, then we have a local minimum point. If the determinant is negative, then there's no extremum point. It's a saddle point, but it's not, I'm not requiring you to write it's a saddle point. It's just you understand that if this determinant is negative, then we say, no, that's not an extremum point. That's it. And if this determinant is 0, then the question remains open and you have to investigate the function in particular. You choose a small neighborhood of that critical point and just investigate a little bit in both x directions and in both y directions, positive, negative, I mean. So basically, we will focus on these first 3 cases, because the 4th case, well, it depends on what you need to do, for what purpose you need to do. If you need to do it for practical purposes, you might use 3-dimensional graphing, any graphing application, GeoGebra, Desmos, whatever. And so let's try it. Let's just try the local extremum points. It's a little bit past time, but, well, unfortunately, this is a necessity altogether, because you know how the test taking happens, because the group was so very large. So a lot of our trouble is because the group is so very large and we couldn't write the test all together at the same time. 60 people at the same time is not something I can manage. And so, all right, let's see. The first derivative with respect to x is 2x plus y minus 3. Do you see how? I hope. So y is held constant. We are only differentiating by x. By now you should. It's only the second lecture with these partial derivatives, so you still have to be careful if you have not practiced so far. I hope you did. Now by y, x plus 2y minus 6. Should be easy. And now we ask that these are 0. We want to ask that these, both of them, are 0. So what do? We solve a system. 2x plus y equals 3. X plus 2y equals 6. If the derivative is 0, I can simply immediately transfer the minus 3 to the right-hand side. Now I have a very small linear system. Because it's a 7th grade school system, you may use school methods for this. You don't have to use Cramer's rule. Sometimes we may use inverse matrix methods. All right. So what we have is, let's multiply the second equation by minus 2 and add to the first one, like Gauss method. 2x minus 2x is 0x, minus 4y plus y is minus 3y, minus 12 plus 3 is minus 9, so y is 3, and that means that x is 0. So our critical point is 0, 3, and the function value would be 0 here, 0 here, 9 here, 0 here, and minus 18 here. 9 minus 18 is minus 9. So Z0 is, of course, Z of 0, 3. So that's how we found this third coordinate of the point on the graph. If I need to find the local extremum point. So now let's see. Well, yeah, maybe this is not an extremum point. Now we have to do the second order derivatives. So second order derivative, both times by x, take this, differentiate by x. So this is 2x plus y minus 3 differentiated by x, it's 2. This is a11 already. Second order partial derivative. Let's differentiate the same thing by y. It's 1. All right, so this is a12. And second order partial derivative both times by y is x plus 2y minus 6. Take y derivative, differentiate by y, it's 2. So our determinant is 2, 1, 1, 2. This is 4 minus 1 greater than 0. So this means there is an extremum point, and we see that a11 is 2, it is positive. So from this, we can make the conclusion that we have a minimum point. So M is a minimum point, M0 is a minimum point with coordinates 0, 3, minus 9. This is the minimum point of the function. Again, you see the totality is not so very complicated. Yes, this is perhaps the biggest task of all. Because first of all, yes, you need to find all 5 derivatives, all 5 partial derivatives, but then you also have to do something with them. So this is probably the largest task possible for functions of 2 variables for now. But the plan is comparatively simple. All that is needed is knowing what to do. By the way, description of this method, the description of all these methods is in the formula sheet. I definitely ask you to print out the formula sheet, keep it on the table in front of you, and use it instead of going to dubious applications. And maybe one example is necessary. One last example is necessary. That will be okay. This will consist of somewhat more complicated derivatives, as you can see. So let's write the derivative with respect to z, 6x squared minus 36y. Z derivative with respect to y is 6y squared minus 36x. So we have to solve a system. See, 6x squared, let's say, equals 36y, and 6y squared equals 36x. So we can simplify a little bit. X squared equals 6y, and y squared equals 6x. So in principle, we could have a look at this and try to understand what is going on. But basically, I could take, for example, anything. I could put, for example, I could take y is x squared divided by 6, put it in the second equation. Now I have x to the 4th divided by 36 is 6x, which means x to the 4th is 216x. So we have two possibilities. X times x cubed minus 216 is 0. So x is 0 or x is 6, because 216 is 6 cubed. Remember how I got this. I basically multiply 36 by 6, so it's 6 cubed. So x is 0 or x is 6. So we have two critical points. We have point M1 where x is 0. In that case, we see that y is also 0. And if x is 0 and y is 0, then z is 430. And the second critical point, if x is 6, then we see that y is also 6, because we see both of them have to be positive. Because x squared is positive, so y must be positive. Y squared is positive, x must be positive, or both zeros. 6, and then we can find the third value. Then we can find the third value, which is not necessary at this moment. But if we need, we can find the point C, the coordinate Z. So now we have 2 points. We still need the second order derivatives. I will find them here. So second order both times by x is 12x. That's it. Second order both times by y is evidently 12y. And second order mixed x by y by x is minus 36. And now I can say that at point M1, if x and y are both zeros, then my determinant will be, now putting zeros, x is 0, y is 0. So these two are actually zeros. So this is 0 and this is 0 because x and y are both zeros. And this is minus 36. This is minus 36. We see that we have 0 minus 36 squared. It's negative 36 squared, but you know that a square is always positive. So this determinant is actually negative. This determinant is actually negative. So we see a negative determinant, which means this is not an extremum. This is a saddle point, actually. This is a saddle point, no extremum. No need to write saddle point, because we are not investigating those further on. Now at the second point. So one thing at M2, let's see, the determinant is, now if we have 6 and 6, 12 times 6 is 72. So I have 72 and 72, and this is still minus 36, minus 36. So we see that this determinant is 72 squared minus 36 squared. It's positive, which means that, yes, we have a minimum or maximum. This is positive, so 72 is greater than 0, which means that M2 is a minimum point, local minimum. And now that we know that, yes, it is an extremum point, we can devote some time to establish the third variable, the z value at this point. I am right now, I don't want to spend more time and hold you even longer than I have already, because there are some people who want to write the elementary mathematics. Now, about test -2, found it? Okay. Thank you. I will trust you because I don't have my solutions open at the moment. So, all right. We have a colleague telling us that this is -2. But of course, if you have a calculator handy, it's easy. All right, now about what comes next. So I'm trying to find an empty board, an empty space, so that I can write down things. So first of all, elementary mathematics, as far as we are, I think is all checked. So some of you have failed, some of you have passed. So basically, for the midterm, first of all, for the midterm, for Friday, for the second midterm. First of all, yes, you need to have elementary mathematics test 3 and elementary mathematics test 4 for this coming midterm in 2 days. That's those who are doing elementary mathematics must have these. That's one requirement. The next one, T4, test 5, test 6. Unfortunately, we don't have much time for retakes, and I haven't had time to finish marking the retake of test 4, and I have not had time to get to test 6. Sorry, but I have other groups, other students who had something urgent just as well. So I am trying to divide my time between all you. So the thing is, okay, I will not put the mark above 0 requirement. So it's enough that you have at least attempted and done something in these 3 tests, test 4, test 5, test 6. I will not demand at this moment that you have got more than 0. Because evidently I will not finish marking these tests quickly enough. I will do my best, but they will be ready probably tomorrow only, because I have some urgent tasks to do as well. So if you have written all these 3 tests, and if you have passed these 2 elementary mathematics, and if you have attended lectures, then you are allowed to write the second midterm. But please, I would like to remind you, let me know the times when you cannot write the midterm, when you have some other things to do. Just like I have other things to do, you have other things to do. If you are free all day tomorrow, fine. Yeah, not tomorrow, on Friday. If you have a specific time when you have to be somewhere, definitely, or when you have another consultation or test or examination, please mention the times when you cannot. Do not tell me I can do it at 2, because maybe at 2 there will be no midterm session. Tell me when you cannot. If you can anytime, so if you don't email me by tonight, I will assume that you can do it anytime. If you email me, then you either tell me I can do it anytime on Friday, or I am very busy, I have something else between 2 and 4. Okay? Because I really need to say, I will set up the groups. There will be 2 groups, not 3, because not everybody can take the midterm. But I need to see the timings before I set the time. I do suspect that one portion will start early at 10, because I don't want to go late into the afternoon, and the other might be at 12, but I am not sure. It depends on what information I get from you, at what times you cannot take. All right, what else? I will try to correct the midterms, the second midterm and the retake of the first midterm, as soon as I can. I guess I will have to sacrifice a part of my weekend, and then on Monday. On Monday, unfortunately, if you have failed both midterm examinations, then nothing doing. You have to write the final exam. If you have failed, let's say we will see Monday, for example, if you have failed 1 and passed 1, then you will be able to retake the failed midterm on Monday. That, of course, does not apply to those people who have already retaken the first midterm, because each midterm can be retaken once. But if you have failed both, then basically there's not much sense trying to retake midterms. It's easier to write in one sitting on Wednesday, to write the final, right? Everything at once. Better an hour and a half than 2 times an hour and a half. So something like this. So in other words, because this is the last time when we actually can talk, all of us together. Okay, so if, let's say, okay, you write it on Friday, Monday you will see, okay, Sunday evening, how I don't want to, but all right. I will try to do it as quickly as possible. If we manage to write the midterm 2 early enough on Friday, I might manage to correct the second midterm by Friday evening. I don't know. I will try. So in principle, if okay, one midterm passed and one midterm failed, if you have taken them once only, of course, both, then you will be able to retake on Monday. Then you will be able to retake on Monday, one of them. Retake Monday. If you have failed both, then I would think it's less trouble for you just to write the final examination. Of course, a lot depends on it, but if you have not learned anything by this point, I am not exactly sure you can manage to cram everything by Wednesday. That's not something I'm sure. So if you have 2 fails for the midterm, then you have to write the final exam on Wednesday. But 1 failed midterm, I will allow a retake on Monday. So there will be a time for the first midterm and a time for the second midterm on Monday, basically around our normal lecture time. Around our normal lecture time. All right. If there is anything else urgent at the moment, then this is the moment when you can ask. If not,
sorry, in the second midterm we will have material from first, fifth, and sixth units.
4, 5, 6, 7. This is 7 already. Yes, all calculus. All calculus, that is limits, derivatives, investigating functions, and functions of 2 variables. So this second part, so starting with limits, functions, derivatives, investigations, all this second part. This is the second midterm, because the first midterm covered the first half, and this is the second half. All right.
Ma'am, test will be in morning session only, na?
Sorry, what?
Exam will be in morning session. Means 10, it will be till 12 o'clock, or it will be in afternoon.
If you let me know when you can, not when you are, let's say, busy with other things that are not entertainment, of course. If you have really some business or some other test or consultation at another time, let me know. I will try to put the exam in the first part of the day. I hope to be able to do it at 10 and at 12. I hope, but it depends on what you tell me. So I am still waiting for information from you. I will try to arrange the timing so that everybody can attend. So those people who know that they will probably not be able to attend because I don't know, mostly those who are absent forever and ever, they don't bother, but the rest of you, please let me know. If you don't let me know today, then tomorrow morning I assume that you can do it anytime. And now we will start elementary mathematics in a little bit. Let's take a little break. Let's take a 20-minute break, okay? Let's take a 20-minute break. And in 20 minutes, we will start with elementary mathematics 4 retake. And then let's see, we will do it at 10:30. So 10:45. So at 11:30, evidently, again, after a break, elementary mathematics 3. I know there are a couple of people who still need elementary mathematics 1. So let's wait a little bit, so we might be able to arrange something Friday after the midterms, because my time is also limited. So today at 10:30, elementary mathematics 4 retake, and at 11:30, elementary mathematics 3 retake. There are still people who need this. And looking at my everything else, I see that there are some people that still need elementary mathematics 1, but that's then for Friday. More or less this. Elementary lecture time will be wait.